Good afternoon, everyone, and welcome to MOS Live. If you're on Zoom, we do have closed captioning available, and you can turn those on by selecting the CC or closed caption button at the bottom of your screen and selecting Show Subtitles. In just a few moments, we'll be meeting our educators who will be taking us through a journey through space. My name is Francisca. I use she and her pronouns, and I'll be your moderator today. And although you see me now, you'll mostly be hearing my voice throughout the rest of the presentation as I share your questions with our educators. If you're watching on Zoom, you can submit your questions using the Q&A button at the bottom of your screen. And if you're watching us on Facebook or YouTube, unfortunately, we are not able to take your questions, but we're so happy to have you here with us, and we hope you enjoy our program. Now that we know how everything will work, I'd like to invite our educators to turn on their cameras and introduce themselves to start.
Hi everyone, my name is Katie. My pronouns are she and her, and today I will be your educator as we talk about telescopes, but I can't do it alone.
Hi everybody, my name is Talia. I also use she, her pronouns, and I'm going to be your pilot today, providing the visuals, which means I think we can spotlight my feed and I'll switch us over to our software.
Awesome, sounds good. We have lots of really awesome visuals for you today because we are talking about some of my favorite telescopes. So my personal top 5 favorite telescopes. And if any of you in the audience watching wants to share what your favorite telescopes are, feel free to throw that into the Q&A. I would love to hear some of your favorites as well. I'm sure there's some overlap. So you can type those in, or if you don't know the name of any telescopes in particular, you can type in just your favorite planet or your favorite topic in astronomy, anything like that to get folks used to using the Q&A. And it's totally fine if not too. If you do have any questions throughout this program, feel free to type them in there and I can pause throughout. All right, so I'll keep going for now. If you think of any, feel free to type it in. And the first one that I want to start with is the Hubble Space Telescope. So this one and the one after are my 2 favorites of all time. And this particular telescope has really changed astronomy completely. It has peered into the farthest reaches of our universe. And so Talia just highlighted its orbit for us. And now we're getting a much closer look. So this particular telescope is in low Earth orbit, which means that it's very close to home. And it's actually above the atmosphere, which helps its ability to see things out in the universe because the atmosphere blocks many different wavelengths of light, including some visible light and some ultraviolet light, which are the wavelengths that Hubble looks in for the most part. And actually, real quick, if we could switch over to the electromagnetic spectrum, just so that I can cover what that is exactly. So different telescopes look in different types of light, and our eyes only pick up one small area, one small part of the entire electromagnetic spectrum, or all of the different wavelengths of light. So what you're looking at here, that rainbow section, is the part of the spectrum that our eyes can actually pick up. Anything that's outside of it, anything that has a higher frequency or a shorter wavelength to the right, so wavelengths like ultraviolet, X-ray, gamma ray, all of those are outside of our vision. Same thing with the longer wavelengths, so infrared, microwave, radio, those are all outside of our vision as well. So we can use instruments on telescopes to pick up these types of light. And depending on what kind of light you're observing, you can learn many different things about an object. So Hubble primarily looks in visible light, but it also looks in a little bit of ultraviolet and some near infrared as well, but primarily visible. Now, it was launched back in 1990. And it's been in operation since. And some of its main kind of mission discoveries have been both near and far. So some objects in our own solar system have been discovered by Hubble. So some of the moons around Pluto and some Kuiper Belt objects, some things around Saturn as well. all from Hubble. And then we can look farther out and we can look at nebulas and other galaxies, and the entire observable universe and its expansion has all been captured thanks to Hubble. So let's dive into some of those pictures. This first one here is actually really awesome because Hubble would be out of commission completely if it weren't for the astronauts on this particular spacewalk. So in honor of International Day of Human Spaceflight, I wanted to highlight this particular spacewalk because shortly after Hubble's launch, they realized after some of the initial pictures were coming back that the pictures were really, really fuzzy and not good at all. And so they realized astronomers, engineers, folks at NASA that worked on Hubble realized there was something wrong with one of the primary mirrors on Hubble. And so they had to send a couple of astronauts, Story Musgrave and Jeff Hoffman, they're the two astronauts pictured here, had to actually go up and engineer a solution to this mirror problem. And you can find there's some other resources that go into the specifics about it if you're really interested into learning optics and how the Hubble actually works. But essentially one of the mirrors was too flat. And so it was scattering or reflecting light improperly, causing the images to come out blurry. So without the help of these astronauts, Hubble would be pretty much broken and deemed, not workable at all. And we wouldn't have any of the awesome images or discoveries that we do today. All right, so I want to dive into some more pictures from Hubble. So the first one is, this is a picture of the Orion Nebula. And in this particular nebula, there are many new stars forming. So this is a star forming nebula. And we can also see some of the beginnings of new solar systems. So if you look, it's kind of hard to describe, but toward the bottom of the image, maybe like 2/3 of the way down in the center area, there's a star that has kind of a blanket of gas and dust around it. So that particular star we know is a baby star because of this blanket of gas and dust around it. It hasn't had enough time to kind of blow away all of that extra material. And so that's just one example, but there are many stars like this in this particular nebula. And this was the first glimpse really at these early solar systems that Hubble was able to give us. Another nebula that Hubble has observed is one of my favorites. It's called the Crab Nebula, and it's the result of a giant star exploding and going supernova. And right at the center there is a high energy object that was left over after the star exploded called a pulsar, and that's what's kind of providing a lot of this light. And again, this is mostly visible light that you're seeing here. We're going to take a look at this same nebula in another kind of light in just a bit. And then the final image that I wanted to highlight is the Hubble Deep Field. This is one of the farthest pictures or rather most comprehensive pictures that Hubble has ever taken. So there are 10,000 galaxies pictured in this image that you're seeing right now. And it takes up a very, very small amount of the sky. So I think it's like the head of a pin that if you were to like hold that out at the end of your hand, that's about how much of the sky this image is actually covering. And there are 10,000 galaxies. And this is a combination of many pictures over long exposures to give us a glimpse in the really far outer reaches of our observable universe. All right, so that's Hubble. There's a whole lot more I could talk about, but I have to move on to my next favorite space telescope, which is called the Chandra X-ray Observatory. And I forgot to mention that Hubble is one of NASA's great observatories, and so is Chandra. So Chandra's orbit is much farther away. It is still in orbit around the Earth, but it's in a much higher orbit, and it takes about 64 hours to orbit around the Earth one time. It's in a very elliptical orbit as well, so it does kind of change its distance. But Chandra looks mostly in X-rays, so that real high energy side of the electromagnetic spectrum. Now, I love this particular telescope because the things that it studies are some of the most extreme events and objects in the entire universe. So things like supernovas, supernova remnants, and black holes, and galaxies that are colliding, and other types of stars that are dying, really high energy stars, all or active galaxies. Those are all studied using the Chandra X-ray Observatory. So I want to show you some pictures from this telescope as well. So this first image you might not recognize, but you've already seen it in this presentation. So that picture of the Crab Nebula that we had up from Hubble, this is the exact same nebula, just looking at it in X-ray light. There are some other wavelengths in here, but the blue part and that object right at the center with the jets, that is all X-ray from Chandra. And so once Chandra pointed at this particular nebula and took a picture, it's super obvious that there is an object sitting right at the center of that galaxy that wasn't, or of that nebula, excuse me, not galaxy, that was not visible in the Hubble picture that we saw earlier. So it's really great because you can take all of these different telescopes and take all of these pictures from different wavelengths of light of the same object and put them together and get a composite image that tells the whole story, right? In that visible image that we were looking at from Hubble, we couldn't see this pulsar, the super, super dense, spinning, energetic object sitting right at the center of that nebula. But when we look at it in X-ray, we can see it. But we also can't see some of the thermal energy coming from this particular nebula either. So it would be worth it to include other wavelengths like infrared, for example. All right, so let's look at some more pictures from Chandra. So this is kind of a collage of a bunch of different high energy events in the universe that Chandra has captured. So if we look in the top row there on the left, that is a galaxy that's kind of viewed from the side, and anything that's in blue and purple in these images is Chandra. And that particular image is showing the shock waves and just high energy particles coming off of supernovas happening in that galaxy. The middle top image is a galaxy cluster, and that blue haziness is X-ray radiation coming from just high energy gases, superheated gases in between this galaxy cluster. And then if we look on the right, that ring there is the shock wave of a supernova, so a star exploding. Then if we move to the bottom left, we can see one of the most volatile star systems that we know about, that astronomers know about at all, called Eta Carinae. And then in the bottom middle, we've got a galaxy that kind of looks like a bullseye. And what you're actually seeing is two galaxies that have collided. So a smaller galaxy that has hit the center of a larger galaxy and sent a massive shock wave out throughout the galaxy that then spurred star formation. So there's tons of new stars that kind of form around that ring in that particular galaxy. And then that last one there, the bottom right, is the remains of a star, of an average star that has run out of fuel and died. So it's just kind of shed its outer layers. Not quite as much of an explosion as a supernova, but it does expand and release outer layers of gas. And some of that is superheated and high energy, which can be picked up by the Chandra X-ray Observatory. And then the final thing that is not pictured in any of those, but Chandra can pick up galaxies that are active. And an active galaxy means that there is a supermassive black hole sitting at the center of that galaxy, which is the case for most galaxies in the universe. But it means that the black hole is actually accreting material. So material is falling into the black hole and it's heating up along the way, causing a massive buildup of electromagnetic radiation and charged particles that eventually get blasted out into space, incredibly high energy that can be seen from either side of an entire galaxy because material is falling into the galaxy's central black hole. So, which I think is just super awesome. These are called quasars, in case anybody's familiar with that term. All right, before I move on to the other telescopes, I want to pause and see if there have been any questions so far.
Yeah, so there is some love for Hubble and some love for another GMP telescope. There's a question about when will Hubble be decommissioned? Is that something we know?
Yeah, so Hubble, I'm not entirely sure of the date. Talia, do you know the date?
There isn't a specific date. It's basically they're going to work that telescope until the wheels fall off, until it literally cannot function anymore. As for when that's going to happen, it is expected to be sometime in the early 2020s. This telescope is 30 years old after all, but nobody has a predicted date. And then once the telescope can't point accurately anymore, we're not going to retrieve it and bring it back down or anything like that. They will try to attempt a controlled reentry if they can, but eventually just over time, Hubble's orbit is going to degrade and it is going to eventually, years after it is decommissioned, re-enter the atmosphere.
But on the bright side of things, it will be replaced not with something similar necessarily, but with the James Webb Space Telescope, which will observe similar things to what Hubble has observed and hopefully be even more powerful. It won't be in the same spot. It's going to be much farther away, like out past the moon. It'll still be orbiting the Earth, but just really far away. But it will serve a similar purpose.
Thank you. And we had another question about how do we measure the energy that's coming from these giant explosions that you talked about?
Yeah, that's a really good question. And basically all of it is done by collecting light. The frequency of light and different wavelengths of light can only penetrate certain, like our atmosphere, for example. Only certain wavelengths of light can actually get through it. So we know that most high energy forms of light are bounced off the atmosphere or redirected by the Earth's magnetosphere. So we know that how certain light acts. We know the effects of certain types of light, like ultraviolet light, for example. If that penetrates our skin, we can get a sunburn. The higher radiation or the higher energy, the more dangerous that light can be to humans. But we have instruments that can actually detect and capture safely these different wavelengths of light, and then that can kind of tell us. So it's all about collecting light from objects that are, many, many light years away. That light had to travel through huge swaths of space to reach our telescopes. But once they have, we can tell how energetic that particular kind of light is with our telescopes.
Thank you. I think that's it with our questions for now.
Great. I will move on to the next two, which are I clumped them together a little bit, but we'll point them out separately. So they are both studying the sun. The first one is the Parker Solar Probe. And the second one that we can point out in a second is the Solar Dynamics Observatory. So the Parker Solar Probe is in a heliocentric orbit. So So far, we've talked about 2 telescopes that are in orbit around the Earth. The Solar Dynamics Observatory is also in orbit around the Earth, but this one is in a sun orbit. So it's orbiting directly around the sun. It was launched back in 2018, and in order to get into its orbit around the sun, since it's heading much closer to the sun than anything that we've ever sent out into space before, it has to figure out, as if it's its own sentient being, engineers and astronomers ahead of time had to figure out how to slow it down. And so they're using Venus. They're using flybys of Venus to help slow this spacecraft down on its way into its kind of final orbit around the sun. So it's going to do 7 total flybys of Venus. It's already done a few already, and then it's going to reach its closest approach to the sun in 2025. It'll be closer than we have ever sent anything, which is super exciting. It'll be within 4.3 million miles of the center of the sun. And so for reference, the Earth is around 93 million miles away from the sun. So it's going to get super close. It's going to be in a very elliptical orbit, so very eccentric. So it'll be much closer to the sun at one end of its orbit than the other. And the reason for that is so that it's never spending too much time in that really, really, really close range, as to not completely destroy all the instruments on board. They are built to withstand the temperatures and radiation from the sun, but not for a super long time. So it is in this very elliptical orbit around the sun. And its goals are to study the outer atmosphere of the sun called the corona. And this particular part of the sun has puzzled astronomers for a while because temperatures are insane in this part of the sun's atmosphere. So the surface of the sun is about 10,000 degrees Fahrenheit, but you get farther out and into the corona, there are some spots of the corona that are just as hot as the core that can get in the millions of degrees. And the mechanism behind this and why temperatures can get so hot is still relatively unknown. And so Parker Solar Probe is going to investigate this, among many other things, like checking out its magnetic field and figuring out why the solar wind moves so fast. And there's a lot of stuff going on there, but it's very exciting. It also made a flyby of Venus. I already mentioned that it had to fly by a few times, but there's one picture in particular that I wanted to share. So it used its instruments on board to take a picture of Venus. And so all of those little streaks that you're seeing are dust particles that are kind of being reflected dust particles or cosmic rays that have gotten in the way of the image. But Venus itself, it's kind of picked up some of the surface of Venus, which is really weird because Venus has an incredibly thick atmosphere. It's about 1,000 times or 100 times thicker than the Earth's atmosphere. And so you can never see the surface unless you use certain types of light that can penetrate the atmosphere and send back signals that you can then map. So with a visible instrument, which is currently what you're looking at, this is visible light. But Parker Solar Probe was able to actually pick up some thermal signatures from the surface of Venus, which was really weird because that's not what the instrument was intended to do. So it could mean a number of things. Maybe the instrument is picking up some infrared light and astronomers never intended necessarily for that, but that would be pretty cool. Or maybe there's something really weird going on with Venus that we don't know about. And so maybe there's a new window to look at Venus and study Venus, which would be super cool also. So either way, it's pretty awesome. So let's talk about the Solar Dynamics Observatory. Again, it's another telescope to study the sun. I love the sun. I love stars. That's why it's on my list. And this telescope is in orbit around the Earth. And its main goal is to study the sun's effect on the Earth. And so it makes sense for it to be much closer to home. So this is what it looks like. And we can also show you a video from the Solar Dynamics Observatory of the sun. And it looks at the sun in all different wavelengths of light. So most of the telescopes we've talked about so far only look in 1 or 2 wavelengths. This one looks at all of them. The one you're currently looking at is extreme ultraviolet, I believe. And so this is our sun over 10 years kind of condensed down. And so you can see it's really weird magnetic field with loops popping out of the surface all over the place. You can occasionally catch a sunspot or parts of the surface that are slightly lower in temperature than other areas. You can see some of its outer corona. It's the plasma that's traveling along these magnetic field lines. And occasionally you can spot a solar flare or a solar prominence where that magnetic field gets all twisted up together and snaps and sends charged particles and radiation out into space. And so there's just a whole bunch of really cool phenomena that is studied through the Solar Dynamics Observatory. So that's why it made the list. And for the final telescope today, this is the only one that is on the surface of the Earth because it is a radio telescope or an array of radio telescopes. So radio waves are able to penetrate the Earth's atmosphere. They are the longest wavelength. And so thus we can study the sun using a radio telescope on a cloudy day from the surface of the Earth, which is pretty cool. But that's not what this telescope was used to do. So this particular telescope is called the Event Horizon Telescope. And again, it's a network or an array of telescopes all around the world to simulate an Earth-sized telescope, because its goal is to take pictures of supermassive black holes that are in galaxy that, well, the first one was in a galaxy that is 53 million light years away. That means it takes light 53 million years to travel from that galaxy and reach us here on the Earth. So in order to resolve an object that is that far away, that's 53 million light years away, we need an Earth-sized telescope. And that's not really possible, so you have to simulate one, which is why they connected all of these radio telescopes together. And so these are all of the abbreviations of various telescopes around the Earth. And then all of their data got sent back to Cambridge, to MIT and the Harvard Smithsonian Center for Astrophysics, where they parsed through all of that data and were able to turn it into a picture that we could see with our eyes, which is insane and so cool. This is the first picture ever of a supermassive black hole in that galaxy that's 53 million light years away. And so that central dark region is the shadow of the black hole, and all of that lit up area around it is material that is essentially accreting into the black hole. It's falling into the black hole. And as it's orbiting, it builds up lots of friction. It's moving at relativistic speeds or close to the speed of light. And so it releases a whole bunch of energy, a lot of light. And we can pick it up with our telescopes, which is what this one has done, specifically radio waves. You could look at this in other wavelengths, of course, but that would require different setups and telescopes in space that are the size of the Earth, which just sounds like a pretty big feat. So maybe it's on the way. Maybe it's being planned. Who knows? So yeah, those are my personal favorite telescopes. We have a minute if anybody has any last minute questions.
It's so cool. And I love seeing that image of the black hole. It's just like, wow, finally. Well, we have one question of like, how do you coordinate all those different Earth radio telescopes?
Honestly, I don't know. I'm not sure how they all work together, the intricacies of how they operate at all. I don't know, Talia, if you have anything to add to it.
It's not simultaneous. Obviously, those telescopes are all over the world. They're not all facing the target at the same time. it involves, and it wasn't like a single day of observing for each telescope either. It was a long period of observing for each telescope, and the amount of data that had to be crunched to create that image is mind-boggling, especially some of the data you might have noticed, and I'll bring the map back up, came from the South Pole telescope. That stuff had to be there. You couldn't transmit that data. There's no good way to transmit. In fact, there was so much data from all of these telescopes that you couldn't really transmit it digitally. They actually had to load it all up on drives and fly it all into Cambridge because it was too much data to transmit electronically. And that was especially difficult for the South Pole telescope. So I don't know how exactly it all came together. I know it was a long-term process involving many hours of observing on different days from each of these telescopes.
And more images coming.
Yes.
Wow. Well, thank you both. We have sadly reached the end of our program, but I hope you can all virtually join me in thanking Talia and Katie for sharing their awesome space knowledge with us. And guys, I'll ask you to both say goodbye and turn off your cameras.
Bye.
Bye, everyone. Thank you.
And for all of you here with us today, thank you for learning with us. Check out NASA's Eyes to explore space on your own, and also join us for more guided explorations every Tuesday. You can find all of our virtual offerings by visiting us online at mos.org/mos@home. And if you enjoyed our program and are able, we hope you'll consider making a donation to the Museum of Science. And you can do that by visiting the link engage.mos.org/welcome, and your support will help us continue this programming. Thank you all and have a good afternoon.